Hello everybody, and welcome to your introduction into right triangles. Now in class, we made what's called a foldable. We made a book that we're going to call our right triangles book. And you're going to want to make sure that you get that made when you get to class if you haven't done so already. And then we're going to start filling in the pages, and this video is designed, I'm talking to you a little bit about how to fill in those pages, and then how to use the information that's going to be in here, at least the first couple of pages. Okay? So this is our right triangle book. On the outside of the right triangle book, you want to title your book Right Triangles. And then we use the cover to also remind us, one, what a right triangle looks like, and the different parts of a right triangle. And so, first things first, you're going to know you're looking at a right triangle. How? Because there should be this right angle box, right? It's not because it looks like one. It's not because this angle looks like it's about 90 degrees. We have to know that an angle in this triangle is 90 degrees. And this right triangle box is one way to get that done. Okay? So once we know we have a right triangle, then we have to remember that the sides of a right triangle have specific names. The two sides surrounding the right angle are called legs. And then the side opposite the right angle has that weird name. It's the hypotenuse, right? The hypotenuse, and we make a quick designation here, is always opposite the right angle. Always, always, always. And one thing that you're going to want to make sure you can do by the end of this unit is when you see a right triangle, the first thing you're going to want to do is go find the hypotenuse. So much depends on the length of that hypotenuse, okay? Or recognizing that this side is the hypotenuse and then the other two sides are legs. Okay, so you got to know those first. Okay? Now, understanding that, we can start to talk a little bit about different theorems and things that we find with right triangles. And so if you open up your book, the very first page of your book is going to be dedicated to what's called the Pythagorean theorem. Now, I don't think this is the first time you've heard the Pythagorean theorem, but what this may be the first time ever hearing is the Pythagorean theorem given to you in a very specific way. Now, the Pythagorean theorem itself is written out here for you, where the Pythagorean theorem itself says that the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. In other words, it says as long as you can pick out the legs and the hypotenuse, then leg squared plus leg squared is going to equal hypotenuse squared. Now, I know you were taught before a squared plus b squared equals c squared, but I really think that you need to get out of that habit of thinking of it as a, b, and c, and start thinking of it as legs and hypotenuse. One, because it's just a way to enforce the vocabulary behind a right triangle, but two, because it can get a little confusing as far as which side's A, which one's B, which one's C. So start thinking about legs and hypotenuse, and what the Pythagorean theorem actually says is leg squared plus leg squared equals hypotenuse squared. Okay? And the next thing we put on this page was just a couple quick examples on how to use the Pythagorean theorem. So this first example here, right, where this side is 10, this is 8, and we want to go find that side. Well, this, that, and that, we got to make sure we understand the names of. So since these two are the legs, and this is the hypotenuse because it's across from the right angle, it's opposite the right angle, our Pythagorean theorem takes this shape. 8 squared plus 10 squared equals x squared. Let me go through and solve. 8 squared is 64, 10 squared is 100, and obviously x squared is just x squared. 100 plus 64 is 164. Then we square root both sides. And we get the square root of 164. Now, because Algebra 2 and pre-calculus are going to have us reducing radicals more often than getting a decimal answer, I want you to get in that habit as well. Start reducing your radicals. Okay, so the square root of 164, and there's a couple of different ways you can go about this. Now, what I talked about in class was this idea of something called an upside down box. I kind of like this method. It's a little bit longer, and it doesn't quite use enough number theory or number sense. Oh, sorry, switched pages here. But it might be an easier way to organize your factors. We're still going to factor 164 down. So we put 164 in an upside down box, and out to the left here, I've got to find the smallest prime number that will go into 164, and that indeed is 2. Got to be prime. Now, 2 into 164 is 82. Since 82 is not prime, I put that in the box, and I'll do the same thing. Smallest prime number to go into 82 is 2. That gives me 41. 41 is prime, so I don't put 41 in a box. What I do instead is, you have to remember this, right? The reason why we're showing factors this way is because we're going to circle our pairs and realize that it takes 2 to break 1 out of jail, right? This guy takes the bullet. This guy actually gets out of jail. So 2 is outside of jail, jail being the radical. Okay, only 1 2 makes it out. And then this 41 didn't have a buddy to help him out, so 41 goes back inside. And so square root of 164 reduces down to 2 square root of 41. And that's what you see here. Okay? Now, another quick example for you, and this is something that I like to show. In case the side that you want to find is not the hypotenuse, you need to understand that the x doesn't always go at the end by itself. So we have this example here where this side is 4, this is x, and this is 9. Now, 4 and x are your legs, so we get 4 squared plus x squared equals 9 squared. Now, 4 squared is 16, x squared is x squared, 9 squared is 81. Now we want to subtract 16 from both sides. And then we get x squared equals 65. We're going to square root both sides, and we get the square root of 65. Okay, so notice that the x went over here by itself in this example, and x was over here with the 4 in this example, and that's because of where x was. X in the first example was the hypotenuse, so that's why it went out here by itself. In the second example, x was a leg, and so it had to go in here with the 4. The other thing I'll do real quick for you is show us our upside down box for 65. Put 65 here in an upside down box. Now 5 will go into 65, and it will go 13 times. 13 is prime, so we can't put, you don't want to put a box in it. And now we're going to look for pairs. There are no pairs. So 5 and 13 would both stay in jail. You're supposed to multiply everything that stays in jail. 5 times 13 is 65, and so this doesn't really reduce, and we leave it at the square root of 65. Okay? There's Pythagorean theorem for you. Now, in a second, we'll switch over and get into the example packet that I handed out in class, and let you do some examples and some different examples on how you can use Pythagorean theorem. Before we get there, though, I want to talk about something called a Pythagorean triple. Okay, a Pythagorean triple is defined as 3 whole numbers. The definition is here. 3 whole numbers that can represent the side lengths of a right triangle. Now, that means it satisfies Pythagorean theorem. Okay, so some Pythagorean triples are 3, 4, 5. 5, 12, 13, and 7, 24, 25. If you were to take 3, 4, 5 and put that into Pythagorean theorem the way it's supposed to go, it would then 3, 4, and 5 would satisfy Pythagorean theorem. In other words, 3, 4, and 5 could be side lengths of a right triangle. The only way that happens is if which length was the hypotenuse. Well, hopefully you're saying to yourself that the 5 would have to be the hypotenuse, because the hypotenuse is always the longest side of a right triangle. So we can test this out. So 5 squared would have to be equal to 3 squared plus 4 squared. Well, 5 squared is 25. 3 squared is 9. 4 squared is 16. And so we get 25 equals 25. So that's what we mean by 3 whole numbers that can be the side lengths of a right triangle or satisfy Pythagorean theorem. Okay? Now, as with humans, right, we all belong to a family. We're related by blood. And so Pythagorean triples can have families as well. And they're related by common factors. So 3, 4, 5 is its own family. And members of that family are just 3 whole numbers that can be the sides of a right triangle. And the way we create those is by applying the same factor to each of 3, 4, and 5. So in other words, 6, 8, and 10 would be a member of the 3, 4, 5 family, because all you do is apply a factor of 2 to 3, 4, and 5. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. So 6, 8, and 10 is a Pythagorean triple itself, but is a member of the 3, 4, 5 family. 9, 12, 15 is a Pythagorean triple itself, but is a member of the 3, 4, 5 family. Okay? And so on and so forth. 5, 12, 13 is its own family, and it has its own members. 35, 84, and 91 would be a member of that triple family. 15, 36, 39 would be a member of that triple family, right? And we would know that by trying to divide out a common factor of our 3 side lengths to see what family it belongs to. Okay? Now, there are a bunch of triples out there, and therefore a bunch of families. 7, 24, 25 is another triple, and it has its own family members. 14, 48, 50 would be a member of the 7, 24, 25 family. Now, how can these triples help us? Well, if you can ever recognize that you're looking at a triple, then you can use that to help find missing side lengths without necessarily having to get into Pythagorean theorem and doing all the squaring and square rooting and all that kind of stuff. For example,